Hello and welcome to this video tutorial for ANSYS Mechanical. The content of this video tutorial is plate meshing and nonlinear material properties. So currently in Creo, I've made a surface feature of just a simple dog bone sample. So this may be a material sample that you might be testing in the material testing stage. So I've made this as a surface model, which means it doesn't have any thickness within Creo. However, when we import it into ANSYS, we can then apply a plate thickness. So we'll launch ANSYS Workbench. And once our model's been imported, we can then drag and drop the static structural toolbox over the geometry. Now, before we get into ANSYS Mechanical, it's important to realize that previously ANSYS has predefined our engineering data, which is fine because we've just been using structural steel. However, if we want to do a nonlinear analysis, we need to use nonlinear material properties. So if we double click the engineering data, so a new tab has opened up in Workbench. We can see there's our structural steel added to our library. We can also add our own material properties using test data. However, we're going to go into engineering data sources because ANSYS has a lot of preloaded engineering materials. So a wide range of general materials, steel, aluminium, cast iron, titanium, nonlinear materials, hyperelastic materials like rubbers, composites, and geomechanical materials as well. So there's quite an extensive library. If we have a look at the general nonlinear materials, if we scroll down, we can see structural steel nonlinear. So we're going to add that to our database by clicking the plus icon, and we can see some properties. So it's important to realize this material has bilinear isotropic hardening properties. So if we look at our stress strain curve here, this structural steel is represented by a curve or a straight line in the linear elastic region, and then another straight line is used to approximate the plastic region. So we can use this to model plastic deformation. Okay, so we don't have to make any changes to this. This is preloaded, but it's always worth checking your data set. Okay, so we can close the engineering data tab, and we can double click on the model to open up ANSYS Mechanical. All right, and there's our dog bone sample. Once again, just making sure our units make sense. Now our geometry has a question mark. This is because currently this model has no thickness. So I'm just going to add a thickness of 1 mil. So this is a plate model. So the reason I'm using a surface model in Creo is it produces a plate model in ANSYS, and that allows us to easily change the thickness on the fly. You know, if we get that wrong, we can come in here and change that. So it's just easy to work with. Now, by default, ANSYS has assigned the structural steel. However, that's our linear material properties only. So we want to select structural steel nonlinear. And we want to make sure our nonlinear effects are ticked to yes. So it will incorporate plastic deformation. Okay, time to have a look at our mesh. So I'll just try a uniform mesh with element size 2 by 2 mil. So we'll see what that looks like. Okay, so that's looking quite good. So we can look at that in plane. So typically when we're doing material testing, we're more interested in what's going on in the neck of this sample. But we could spend a bit more time tidying up some of these radii, but this is fine for the time being. Okay, we can leave the mesh as is. That was a uniform function, setting the element size to 2 by 2 mil. We can now look in static structural. So we want to apply supports. So we'll put a fixed support at the bottom here. And this is going to be a tensile test. So our sample is going to get pulled up in the y direction. Actually, before we do that, in our analysis settings, we're going to use 2 steps. So for some reason, ANSYS uses this time convention. However, this solution is time independent. What I mean by these 2 time steps is for the first time step, the load will be applied and the specimen will be deformed. And in the second time step, the load will be released and the sample will be able to relax into its deformed state. We're also going to turn large deflections on. And we're going to change time stepping to on. And we're going to put in 20 sub-steps. So a minimum of 20 and a maximum of 50. So what this does is it divides the initial load up into increments of 20, gradually applies the load, calculates the deformations in the mesh and the geometry, then applies another 20th, checks the deformations. So instead of solving it once, we're solving it 20 times incrementally. If for some reason the solution doesn't converge, it will automatically put in up to 50 time steps. Beyond that, the solution would have failed and we'll get an error. So sub-steps on and large deflections on. And in nonlinear controls, we'll keep this solver as is by program controlled. Okay, so if we go back to our fixed support here, so this is fixed for all time steps. However, if we apply a load, a force, this top edge here, and we'll go components, and we want to go, let's try 4,000 newtons in the y direction. So at step 0, there's no load applied. At step 1, it will ramp up to 4,000 newtons. And at step 2, we want this load to be released. So we can edit this table and apply a load of 0 newtons. So we can see our load path. It's going to apply the full load and released over a period of 20 time steps. And I'll just apply my geometry. Okay, we're ready to solve. So we made the geometry as a surface model. We included nonlinear properties. In ANSYS, we applied a plate thickness of 1 millimeter. We did some meshing, and then we fixed, or we restrained the bottom surface and have applied a force to the top. So let's right click, solve. And this will take a bit longer. We can view that under solution information And for the solver output, we can have a look at force convergence. Okay, so our solver has converged. It took a little bit longer than the default 20, but this was still quite a quick solve. Nonlinear solves are prone to errors, so always check your message log. Then we're going to add a total deformation scale. So that's to form 16 millimeters. So that's quite significant. So we have a unit length of 100 millimeters from memory, and it's deformed 16 mil. Okay, so we've had a look at our deformation of 16 millimeters. Now this is currently displaying, if we look under options, the last time step. So if we change that to time step 1, when the load is at a maximum, we can then retrieve that result. So when our total load of 4,000 newtons has been applied, it deflects by 17 mil. When we release that and we change our time step to time step 2, it's relaxed by about 1 millimeter. So it's undergone 16 mil of plastic deformation. We can also have a look at stresses. So insert an equivalent stress. And we'll change the time to the first time step. So this is when our full load has been applied. So maximum stress in the neck region. So it's all making sense. And that's well beyond the yield strength at 466 MPa. If we change the display time to 2 seconds, then reevaluate that, so we can see the residual stresses still left in part of the sample. And we should also be able to animate that. I'll just increase the time frame. So the load's being gradually applied, the developed stresses are increasing, then it's released, and there is some degree of relaxation. Okay, so that was a fairly quick look at nonlinear solves. The key things to remember is that our material properties have to include some nonlinear information in the plastic region. In our material properties, or in our geometry properties, we have to include nonlinear effects. The setup is pretty standard in terms of making our force and our restraints. But in the analysis, we need to include substepping and then make sure that large deflections are on. And then when we view our results, remember we can change the time if it's the first or second time step.